one-dimensional heat transfer element. In structural problem, displacement at each node point is obtained. By using these displacement solutions, stresses and strains are calculated for each element. In structural problem, the unknown are represented by components of the vector field. For example, in a two-dimensional plane, the unknown quantity is the vector field u of x comma y, where u is a 2 into 1 displacement vector. Heat transfer can be defined as the transmission of energy from one region to another region due to temperature differences. A knowledge of the temperature distribution within a body is important in many engineering problems. There are three modes of heat transfer: conduction, convection, radiation. Strong form for heat conduction in one dimensional with arbitrary boundary conditions. The following same procedure as in section. The portion of the boundary where temperature is prescribed, that is, essential boundary, is denoted by T, and the boundary where flux is prescribed in recommended for science and engineering track, denoted by Q. These are the boundaries with natural boundaries. And the boundaries are complementary. So Q is equal to 1 by 4th Q by T power 4. With a unit normal used in, we can express the natural frequency conditions as Qn power 1 power 4 Q. For example, positive flux Q causes heat flow negative Q. On the left boundary point Qn power 1 by 4, and heat outflow is positive Q. On the right boundary point Qn 1 power 4 Q into 1 power 4 into Q. Strong form for one-dimensional heat conduction. Weak form for heat conduction in one dimension with arbitrary boundary conditions. We again multiply the first two equations in the strong form by weight function and integrate over the domains over which they hold. The domain for the differential equation and the domain Q for the flux boundary conditions, which yield Ws dx with W 1 by 4. Recalling that W 1 by 4 and T and combining with gives weak form for one-dimensional heat conduction problems. Find 2U such that notice the similarities. Application to heat transfer to two-dimensional. Strong form for two-dimensional boundary value problem. The equations developed in this chapter. For heat conduction, diffusion and elasticity problem are all of the following forms. Such one-dimensional problems are called two-point boundary value problems. Gives the boundary meaning of the above variables and parameters for several applications. The natural boundary conditions can also be generalized as P power 1 power 4 0 on. The equation is a natural boundary conditions because derivative of solution appears in it. It reduces the standard natural frequency conditions considered in the previous sections when we delta x p power p 1 by 4. Notice that essential boundary conditions can be recovered as a limiting case of when v rho x rho is a penalty parameter, that is a large number in this case. Equation is called generalized boundary conditions. An example of the above generalized boundary condition is an elastic bar with a spring attached as shown. where 1 by 4k is the spring constant. If the spring stiffness is set to very large value, the above boundary conditions enforces 1 for u. If we let k 1 by 4, the above boundary conditions corresponds to the prescribed traction boundary. In practice, such generalized boundary conditions are often used to model the influence of surroundings. For example, if the bar is a simplified model of a building and its foundations, the spring can represent the stiffness of the soil. The 2-point boundary value problem with generalized boundary conditions. Another example of application of this boundary condition is convective heat transfer, where energy is transformed between surface of the wall and the surrounding medium. Suppose convective heat transfer occurs at x1 by 4L. Let T into delta P be the wall thickness at x power 1 by 4 and T be the temperature in the medium. Then the flux, the boundary x power x1 by 4 is given by Q del L P 1 by 4. So B del L P 1 by 4 H in the boundary conditions, where H is convection coefficient with the dimension of W m square degree per degree Celsius. Note that when the convection coefficient is very large, the temperature T is immediately felt at x power 1 by 4, and the essential boundary conditions is against enforced as a limiting case of natural boundary conditions.